So the final video on chapter 3 is going to be on vector components. And this is actually the way we typically deal with vectors in physics class. Okay, so what do we mean by components? So the thing to remember, right, so if you remember our graphical methods and the tip to tail, so that was in the previous video, your textbook also talks about the parallelogram method. But however you think about it, so if vectors are parallel, so if they're in the same or opposite directions, adding them is easy. Or even if vectors are perpendicular, so if they're at right angles, adding is pretty easy because it forms a right triangle and you can use Pythagorean theorem and all the trigonometry you know and love. So the idea behind components is that you rewrite any arbitrary vector pointing off in some random direction just to make sure that all of your addition and subtraction boils down to adding parallel and perpendicular vectors. So that's the point. So let's say we have some vectors. So that's the vector in blue here. So it's pointing off in some random direction. So we're going to write, so this is vector A. So we're going to write this vector A as the sum of two different vectors. So one of these vectors in green, so that's in the horizontal direction. So we're going to call that the x component. So that's our x component. And then vector B, a sub y, so this is in the vertical direction, so we're going to call that our a sub y component. So now vector A is equivalent to the sum of this a sub x component plus the a sub y component. So since they're equivalent, it doesn't matter whether when I'm adding and subtracting or scalar multiplying or whatever it is, it doesn't matter whether I use vector A or whether I use vector a sub x plus a sub y. Either one works. But if I do everything in terms of these components, then all my addition and subtraction winds up as adding parallel and perpendicular vectors. Okay, so and just a note here, so on three-dimensional vectors, so remember, so we started off actually chapter 2, we actually had one-dimensional vectors, but one-dimensional vectors are pretty trivial, so it's just a single component, right? And so typically we just use x to indicate us the single component. Sometimes we used y if we were moving in the verticals, if we were moving along a vertical line. And directions are easy because you're moving along a line, so that's just your one dimension, so you can just use positive and negative. Now for two-dimensional motion, we need two-dimensional vectors which have two components. And typically the two components, we call this x and y. So like if we have projectile motion, typically x is in the horizontal direction, y is going to be in the vertical direction. Now, on occasion we will use three-dimensional vectors, but we'll usually just stick to 2 dimensions. But if you understand how to do vectors in 2 dimensions, going to 3 dimensions isn't too hard because it's just adding one more component. So we've got 3 components, and again, in a Cartesian coordinate system is x, y, and z. So, and in principle, I mean, we're never going to get to more dimensions than this in our class, but you can go to 4 or 5, you can go to arbitrary numbers of dimensions, and all it is, you're just adding more components each and every time. Okay, so how do we add vectors with components? Well, first of all, of course, we need to choose our coordinate system. So, and again, assume we have a Cartesian coordinate system. So figure out the x-axis, the y-axis, and which is going to be the positive x and y and negative x and y directions. Again, typically this is going to be horizontal is going to be x, to the right will be positive, vertical direction will be the y-axis, and up will be positive. So we want to write all vectors in terms of these components. So we have some vector pointing off in some arbitrary direction. We need to rewrite that as the sum of an x component and a y component. So then if we're adding a bunch of these together, so the x component of our resultant is going to be the sum of the x components of all the vectors we started with, or all the vectors we're adding together. Similarly, the y component of our resultant is just the sum of the y components of all the vectors that we're adding together. So, and then depending on what you want for the answer and what you're going to do with it, so oftentimes you'll just leave your answer in terms of components. So when it comes to vectors, actually just dealing with the components is usually the easiest way to handle vectors. So unless there's good reason to find a magnitude and a direction for the resultant, it's often you might as well just leave it in terms of the components. Okay, and also a little note here on unit vectors. So by definition, a unit vector is a vector with a magnitude of 1. or that's also called unit magnitude. So it has a magnitude of 1, and it's convenient to have sort of these standard unit vectors that are going to point in the x, y, and z directions, since that's almost always the directions we need to worry ourselves with. So these x and y and z, these unit vectors pointing in the x, y, and z directions. So first off, a unit vector is denoted with a little hat over it, this little caret. So, and the unit vector pointing in the positive x direction is the I hat vector. The unit vector pointing in the positive y direction is the j hat vector. And the unit vector pointing in the positive z direction is the k hat vector. So, for example, if I have some vector A, and let's say this is 3 dimensions now, so I've got an x component, y component, z component. And remember, if I write things this way, so these are called vector components. So the a sub x component is a vector, the a sub y component is a vector, the a sub z component is also a vector. Now, I can also write this in terms of scalar components. So, and for the scalar components, I need to use these unit vectors. So, I've got some scalar a sub x, so, and this is really the magnitude of the a sub x component, vector component, and again, plus or minus would indicate the direction. So, and I've got the I hat indicates that this is pointing, this is in the x direction. And then I've got some scalar a sub y in the j hat or y direction, and a sub z in the k hat or z direction. And so these are called scalar components. This is called vector components. And remember, it's all exactly equivalent. So typically, though, when it comes to actually doing math with these things, it's usually most convenient to write these scalar components in terms of the unit vectors. Okay, and just a quick summary. So working with components, so we're going to do an example in class, but just, so assume we have 2-dimensional vectors, so only 2 components to worry about. So if we have scalar multiplication, so the resultant of some scalar s times a vector a, you just take your scalar and multiply it by the individual components. So s times the x component of a, s times the y component of a. So if we're adding, so we have our resultant is the sum of vector a plus vector b. Well, we just add our x components, so the x component of a plus the x component of b in I hat or x direction, and x or y component of a plus the y component of b in the j hat or in the y direction. And again, subtraction, well, subtracting, we're just adding the opposite, or we're actually subtracting the x components and the y components. Now, if we want the magnitude of vector A, right, so that's absolute value bars, or remember, without the arrow indicates the magnitude, and that is really just the Pythagorean theorem. So A is your hypotenuse, and x and y are the 2 legs of the triangle. So the magnitude is always a sub x squared plus a sub y squared, and you take the square root of that. And if we want the direction of this vector given in turn that we have in the form of components, we take the inverse tangent of the y component or the x component. So one note here, so if you define it this way, so this angle theta is the standard angle. And remember, the convention for this standard angle is you measure it counterclockwise from the positive x-axis. Personally, when I'm giving some angle to determine the direction of one of these things, I just like to draw myself a little sketch so I know what directions or things are pointing, so I can make sure I give the proper angle.